This is the 23rd lecture on general network analysis, and this, as I had commented earlier, shall mark the conclusion of the part on circuits of this course. And today's and tomorrow's lecture we shall concentrate on this, and then the third lecture from today shall be on electronic circuits. So far we have only considered very simple networks in which elements are connected in series or in parallel or in series parallel. It is time now to extend these concepts to general networks in which the connections are more complicated than series or parallel. If there are two elements in series, you can always combine them. If there are two resistances in series, you can combine them into a single resistance. If there is an inductor and a capacitor in series, you can find a single impedance by adding the two impedances. Similarly for parallel networks. Now in general, in making these simplifications or in analyzing complicated circuits which cannot be done by inspection, several theorems are useful, and one of them is the so-called superposition theorem. Superposition theorem, when it was stated, we had not made any constraint on the nature of the elements, whether they are resistive, inductive or capacitive, or even with active elements. Superposition always holds. In other words, the response due to a number of sources is equal to the superposition or the algebraic addition of the responses due to individual sources with all other sources killed. Killed means that if it is a voltage source, ideal voltage source, it should be short circuited. If it is an ideal current source, it should be open circuited. But there is one class of sources which you must leave intact. What are they? The dependent sources. Very good. We shall illustrate, we know that superposition holds for all kinds of sources, but we shall illustrate this with the help of a simple example. This example, I have taken it from the book. We have a voltage source V of t, which consists of a DC voltage 120 plus an AC 120 root 2 cosine of 1000 t. This is one of the problems in the tutorial sheet, in fact. And then we have an inductance whose reactance is specified, and therefore its impedance shall be, if it is inductance, then the impedance shall be J times 20, and obviously this impedance is valid only at the given frequency of interest, that is 1000 radians per second. And then we have a 16 ohm. Whenever a capacitance and its reactance is specified, it is your responsibility to insert the sign. The impedance of this obviously shall be minus J16, and then you have a 20 ohm resistor and a 60 ohm reactance inductor, and it is this current IL of t which is of interest. All right. Since the source, and we want to do this by utilizing the theorem of superposition, or the superposition theorem. Since the source consists of two sources, one is 120 a DC and the other an AC, we can find out the response IL in two steps. That is, I write IL as I1 plus I2, I1 due to the DC source and I2 due to the AC source, and we can combine the two. As far as DC is concerned, you notice that this is a short circuit inductor, the capacitor is an open circuit, and this inductor is a short circuit, and therefore I1 you can very easily see is 120 divided by 20 ohms, that is I1 is 6 amperes. To find out I2 now, you forget about the DC part, and because it is a pure AC, you can apply the phasor relationship. And if I draw the phasor equivalent circuit, what I shall have is a voltage phasor which is 120, the RMS value, angle 0 degree. Then we have, now you talk in terms of impedance, because this is what you shall have to manipulate, J times 20 and then minus J times 16, and now it is 20 and plus J times 60, and this phasor is I2, all right, and I2 can now be written down by inspection. I2 can be written down by inspection. It is the voltage 120 phasor divided by the total impedance looking from here, which is J20 plus the parallel combination of minus J16 and 20 plus J60, and therefore minus J16 multiplied by 20 plus J60 divided by 20 plus J60 minus J16, so 20 plus J44 multiplied by, this is the total current phasor, then it makes a division between two branches, and therefore this shall be multiplied by minus J16, the impedance of the other branch, divided by the total of these impedances, which is 20 plus J44. All right, this you can write down by inspection. Now the next task is to simplify, and if I leave the algebra to you, the final the final result is, well, I2 bar becomes equal to minus 12 root 2 1 plus J. I hope I am right. Yeah, minus 12 root 2 1 plus J, and therefore I can write I2 as a function of time as 24 root 2 will come from 1 plus J, and therefore I think it is simply minus 12 1 plus J. This is the correct result. I am sorry, I made a mistake. And therefore the peak value, the root mean squared value, will be 12 times root 2, then you multiply by root 2 to find out the maximum value, so it is 24. Then you have cosine of 1000 t plus now the angle. It is minus 135 degrees. I explained, let me explain why it is so. The negative sign gives rise to an angle of pi, and 1 plus J gives rise to an angle of 45. So it is either 180 plus 45 or minus 180 plus 45. The angles are the same, plus 225 degree and minus 135 degrees. All right. This angle is the same as this angle, 180 plus 45 or minus 180 plus 45, which means minus 135. And this is the correct answer. Well, the answer as far as mathematics is concerned, both answers are correct, because the angle is the same, plus 225 and minus 135. But one shows that the current is leading the voltage, the other shows that the current is lagging the voltage. And in this particular case, the current is indeed lagging, and therefore this is the correct answer arrived at from physical considerations. This is the point that I wished to make in this exercise. If I take the same problem, namely to find out the current, let me draw it again, 120 0 degree, J20 minus J16, 20 and J60, and the problem is to find out this current I2. I could also have done this by application of either Thevenin's or Norton's theorem. Thevenin's and Norton's theorems are valid for AC phasors also, and these are also very important tools for determining for solving a complicated network. For example, if I apply, let us say, Norton's theorem to find out this current, all right, then you see, you short circuit this, find out the short circuit current, and then you find the equivalent Thevenin impedance, all right. This can be done, but can you suggest a better procedure? Source transformation. What we do is we first apply Norton's theorem to the left of these two lines, then we get 120 0 degree divided by J20, and therefore it would be 6 divided by J. This is a current source, all right. If I apply Norton's to the left of this current source in parallel with J20, this comes in parallel with minus J16, and therefore the equivalent admittance J20, they are not the sum of the two. You have to take the admittance and then take the sum. Therefore 1 by J20 minus J16, which is 1 by J, well, you can simplify this, whatever the result is, that is what you have to put here, a single admittance. Is this clear? J20 impedance comes in parallel with minus J16, whose equivalent impedance would be, you can either calculate by admittances or by impedance. For example, J20 multiplied by minus J16 divided by J4, this is the equivalent impedance, all right. Then you have the 20 ohms and J60, all right. You could now apply the formula for division of current directly, isn't that right? There is a current source which divides into two parts, this one, and therefore you could write the current I2 phasor directly from this circuit. By inspection, nothing is to be solved. All that we are doing now is almost by inspection. We are not solving any differential equation. We are not making even large scale algebraic simplifications. We are going almost by inspection. This is the beauty of the phasor analysis, that it affords network analysis almost by inspection. So the end result is that given any network n which consists of sources and linear elements, well, Thevenin's theorem says that it can be reduced to a voltage source Vt in series with not a resistance now, because it could contain inductance, capacitance and resistance, and therefore some impedance Zt. This is equivalent to this, or you could also work in terms of It, the Norton equivalence, in parallel with the same impedance Zt, all right. And as I said, this affords simplification, tremendous simplification, and whether it is DC or AC, it does not matter. If it is a combination, well, you can work in terms of superposition, all right. The point is, if you have a load to be connected to the network N, if you have a load, let us say ZL, we ask the question, under what condition, if you have a load ZL which is fixed, no, if you have a load ZL which, let us say, varies, the network is fixed, the network contains sources and inductance, capacitance, resistance, all right. Under what condition will the load absorb the maximum possible power from the network? And this, This is in the literature known as the maximum power transfer theorem, or simply maximum power theorem. All right. It's very easy to show that if the network was resistive, then the load should also be purely resistive and should be equal to the Thevenin equivalent resistance of the network. This is the condition for maximum power transfer if capital N is resistive. All right. If capital N contains resistances as well as reactances, then the condition is that the load ZL, if the Thevenin equivalent resistance is G sub G, then ZL should be the complex conjugate of the generator impedance, complex conjugate of the equivalent Thevenin impedance, and this is what we are going to prove in a few lines. We will take a shortcut to the proof, and these are some tricks of the trade. Well, let us replace the network N by a voltage source Vg and an impedance Z sub G. Well, this is a phasor, and we connect it to the load ZL. Then the current in the circuit I, this represents the network N. This is the Thevenin equivalent. The current in the current phasor in this circuit is Vg phasor divided by Z sub G plus ZL. All right. So that the magnitude of the current, magnitude of the phasor is given by magnitude of the voltage phasor divided by square root of Rg plus RL. Now we are breaking up the impedances into their real and imaginary parts, that is resistive and reactive parts, plus J times Xg plus XL, I beg your pardon, square of this, because we are finding out the current. All right. Let me write it down again. The current phasor magnitude is equal to the voltage phasor magnitude divided by square root of Rg plus RL whole squared plus Xg plus XL whole squared. So if I wish to find out the current, the power absorbed by the load, well, the power would be absorbed by the resistive component of the load. Power would be absorbed by the resistive component of the load. Power is stored in the reactive components of the load. So the power absorbed by the load, if I call this PL, would be simply this squared, current squared, multiplied by the resistive component of the load, which is RL, and therefore what will happen is this will be squared, it will be multiplied by RL, and this square root shall go. This will be the expression for the power. All right. And we wish to maximize this power. The problem now is maximize PL by varying the load, that is RL and XL. Let me write it down clearly. Vg squared RL divided by Rg plus RL whole squared plus Xg plus XL whole squared. And since there are two variables, namely the resistive part of the load and the reactive part of the load, PL is a multivariable function. It is a function of two variables. All right, and therefore any maximization that I do shall require partial differentiation. But I want to avoid all this by applying a little bit of trick. The trick is, I argue, let us first look at XL. Let us keep RL constant, let us vary XL. This is what we mean by partial differentiation. In partial differentiation, one of the variables is assumed constant, you differentiate with respect to the other. So if I concentrate my attention on XL, you notice that this PL is a monotonically decreasing function of XL. That is, you increase XL, PL decreases, and therefore PL will be maximized if XL is the variable. PL will be maximized when Xg is equal to minus XL. That is, the minimum value that this expression can take is 0, and it happens when Xg is equal to minus XL. That is, if the source is inductive, then the load should be capacitive. The reactances should be equal and opposite of each other. On the other hand, if the source is capacitive, then the load should be inductive. This is the only way that they can cancel each other, and therefore one of the conditions is therefore that Xg is equal to minus XL. And then under this condition we have not got the maximum power but a sub-optimum, because we have attacked only one variable. We have attacked with only one weapon, whereas we have two in our hand. All right, one weapon has given us the intermediate expression, which is Vg squared RL divided by Rg plus RL whole squared. This has been obtained under the condition that Xg equal to minus XL. Now we argue, how do I maximize with respect to RL? I can again differentiate and put the result equal to 0, but a shortcut is this, and I want you to remember this. I can write this as Vg squared. Now I expand this and divide by RL, so that the variable is brought completely into the denominator. So I get Rg squared by RL plus RL squared divided by RL, so it would be simply RL plus twice Rg RL divided by RL, so twice Rg, of which you see this quantity is a constant, this quantity is a constant, and this is the thing that is variable. Whenever you have an expression of this form, a by x plus x by b, that is, whenever this you should remember throughout your life, that whenever you have an expression in which the variable, one of the components increases with the variable, the other component decreases, then the optimum, that means the minimum, is obtained when the two are equal. You can verify this by differentiation, that is, ddRL of this expression would be 1 minus Rg squared divided by RL squared, and if you put this equal to 0, obviously what you get is Rg equal to RL. Is that all right? No differentiation is needed. If you can put it in this form, then the minimum value of this, not maximum, mind you. Maximum obviously is infinity. When RL goes to infinity, the maximum is infinity, or RL goes to 0. Maxima occurs at both extremes, RL equal to 0, RL equal to infinity. In either case the power absorbed is 0, however. Is that clear? Why? If the load is a short circuit, it cannot absorb any power. If the load is open, no current can flow, so no power can. And therefore this quantity is a minimum when Rg equal to RL, and therefore the power is a maximum, and therefore we can write PL max, PL equal to PL max equal to Vg squared. If you put Rg equal to RL, then you get Vg squared by 4 Rg, Vg squared by 4 Rg. Why? Because Rg equal to RL, so twice Rg whole squared is 4 Rg squared, and cancels with RL, so 4 Rg, and this is called the MAP, the maximum available power from the source. You cannot draw more than this. Under no circumstances can you draw more power than this, and this happens when RL equals to Rg and XL equal to minus Xg. In other words, ZL, which is RL plus JXL, RL plus JXL is simply equal to Rg minus JXG, which is equal to the complex conjugate of the source impedance, and this is one of the most important theorems in electrical engineering. Maximum power transfer. Wherever the power is limited, for example, the signal received through a communication receiver, wherever the power is limited, you should try to draw the maximum available power by matching. This is called impedance matching, that is, by taking a load, by designing the receiver in such a manner that it matches the antenna through which the signal is received. Well, the antenna can be considered as a signal source because it it absorbs the radiation from the atmosphere and then passes it on to your receiver, and this process is known as impedance matching. Impedance matching is not of importance in, for example, lighting of this room or in drawing power for the refrigerator. You don't match the impedances. Why? Because what is of concern there is efficiency. In such cases where maximum power is required, we don't care about efficiency. What is the efficiency under this condition when maximum power is being drawn? The maximum available power is this. An equal amount of power is being absorbed in the source. Isn't that right? You see, the source delivers through a resistance to a load RL. And when the load and source are matched, that is, one is the complex conjugate of the other, RL absorbs this amount of power. This amount of power must then be absorbed by RG also. So half of the power is wasted in the source. We don't want this for an ordinary domestic supply, for example. We don't want this. We want efficiency. And therefore, where efficiency is not important, impedance matching becomes extremely important. And this is one of the most important theorems of electrical engineering and finds application almost everywhere in all fields of electrical engineering. Let me illustrate this with the help of a problem. I have a source 200 0 degree and an impedance consisting of 10 ohms and J10, which means an inductive reactance, and my load is here. My load is this Z, which is shunted by a reactance of an impedance of minus J10, which is that of a capacitor, and a current source which is 10 angle 90. All right. The question is, what should this impedance be? What should this impedance be so that it absorbs the maximum available power? Now you notice that here there are two sources, not one. One fine point is that both these sources, when I write sources like this, what is the information that is hidden in this? Pardon me? They can become? They can be combined. They have the same? That is correct. This is the information that is hidden. Well, you can combine sources in many ways, but whenever we write like this, it means that they are at the same frequency. Otherwise, the phase shall be different. Not only that, if there are two sources of different frequencies, they cannot be combined. Yeah, Rajat's answer is also correct to some extent, that they can be combined, but they can be combined. One of the necessary conditions, not sufficient. One of the necessary conditions is that they must be of the same frequency. All right.
Can they be combined in this case?
Yes, of course. Of course. We will apply Norton's to the left of this, and I shall combine that current generator with this current generator. Surely, no problem. But the question here is different. Do I have to combine? No. The question is, what is Z for maximum power absorption by Z? For maximum power in the load. All that we require is to find out the Thevenin equivalent impedance, which means, what is this impedance? It is simply J10, then 10 ohm. The source is to be killed in parallel with minus J10. That's all. Now if you think blindly, one can think while one closes his eyes, so thinking blindly is not an impossibility, but don't do so. Look at the problem carefully. You don't need to find out, you don't need to combine sources, because all that is asked is what should be the value of Z so that maximum power is absorbed. So you find out ZT. Obviously your ZT is minus J10 multiplied by 10 plus J10 divided by 10, alright, 10 plus J10 minus J10, they cancel each other. So you get minus J10 1 plus J, which is equal to 10 minus 10J. Is that okay? Therefore, all that you need is Z should be equal to 10 plus 10J. In other words, the source is now capacitive because the reactance is negative, and therefore your load should be inductive, and they should match each other. The resistive components should be equal, the reactive components should be equal and opposite of each other. Let's look at something else. Now we are going to the enunciation of another theorem which we have not been familiar with so far. Let's look at a typical problem. Let's say we have a network like this. What would you call this network? It's a 2-port. How many ports? 1 and 2. But it is also a 3-terminal network because there are only 3 terminals, 1, 2 and 3. This terminal is common between input and output. Alright. Now let's apply a voltage source here, V1, and let's find out the short circuit current I1 here. Alright. Obviously I can find out I1 by inspection. It is V1 divided by Z1 plus Z2 Z3 divided by Z2 plus Z3. This is the total current. Then I take current division between Z3 and Z2, and therefore this is Z3 divided by Z2 plus Z3. Agreed? Is it okay? Alright. So therefore I1 by V1 is equal to, well, you can see that it is Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1. Is that okay? Is this algebra all right? Okay. Now let me give a name to this quantity. You see the current is obtained here at a port which is different from the exciting port. The excitation is at port 1 and the response is obtained at port 2. The ratio of the response to the excitation is now an admittance. Isn't that right? The response is a current and the excitation is a voltage, and therefore current to voltage has the dimension of admittance, and this is called a transfer admittance. Transfer, because the current response is obtained at a different port, and the symbol that is used for it is Y12. That is, this is the exciting port, port 1, and the current is obtained at port 2. There are different conventions. Y12 is the response obtained, the current response at port 2 divided by the voltage excitation at port 1, and it is called transfer admittance. You understand the meaning of transfer? If it was not transfer, if we had applied the voltage at a port and measured the current at the same port, then we simply call this an admittance. Or sometimes, to distinguish between transfer admittance and simple admittance, we may also call the latter as driving point admittance. That is, admittance is measured at the port at which you are driving. Alright. If the excitation and response are at the same point, then the ratio of the response to excitation, there is nothing sacred about voltage excitation. You could also have a current excitation and measure the voltage, all right. Then the response to excitation would have been an impedance, all right. So these are called driving point impedance or driving point admittance, in contrast to transfer impedance. Here also I could have a voltage generator, I could have a current generator here, and I could have measured the open circuit voltage. So in that case it would have been transfer impedance. All right. Transfer impedance and driving point impedance, these are two different kinds of quantities, although dimensionally they are the same. If it is impedance, then it is measured in ohms. If it is admittance, then it is measured in mhos. But physically they are different quantities, because the response is measured at a different port in the case of transfer impedance or admittance. Did I tell you the common name for impedance and admittance? Immittance, and this is derived like this: impedance, admittance. What we do is we eat away a part of it. This part is eaten away. So if we want to say transfer impedance or admittance, we'll say transfer immittance, all right, or driving point immittance. Now let me go back to the circuit. I found out here that the transfer admittance is obtained as Z3 divided by Z1, Z2 plus Z2, Z3 plus Z3, Z1. Now let's interchange the source, the excitation and the response ports. Let's interchange. That means I have the same network Z1, Z2 and Z3. I apply the voltage source here, let's say a different voltage source V2, and the response is obtained at port 1. Let's call this as current I2. Do you see what I have done? I have simply interchanged the excitation and the response points. Initially the voltage source was here, and this was short circuited. Now I have transferred the voltage source to port 2, and I am measuring the current at port 1. Now can you find out I2 bar? The same way, it is V2 bar divided by Z2 plus Z1 Z3 divided by Z1 plus Z3. This is the current through Z2. It will come to be the same. That is correct. This would be Z3 divided by Z1 plus Z3, and you see that I2 divided by V2. What should we call this now? Y2 1. Is that correct? 2 1, yes. the source at port 2 and the response at port 1, and you see that surprisingly this is the same. This is the same as in the previous case, all right, and this is what is generalized to a theorem called the theorem of reciprocity or reciprocity theorem. Reciprocity theorem. It in general terms it simply means the following, that if there is a network which contains bilateral elements, let me introduce this term, bilateral, that is elements which conduct equally well in both directions. A resistance, it does not matter whether one end is positive or one end is negative. If the same voltage is applied, the same current should flow, and the resistance conducts equally well in both directions. Similarly an inductance, similarly a capacitance. But you know at least one case, one element which defies this, that is a diode. So if a network does not contain unilateral elements like a diode, if it contains only bilateral elements, then the network is said to be reciprocal. That is, if the excitation and the response are interchanged, then the ratio remains the same. All right, this is called the theorem of reciprocity or the reciprocity theorem, and in the context one must remember that the network should not contain any element which is partial to polarity, which is partial to polarity. For example, a diode, if it is forward biased, it conducts easily. If it is reverse biased, it does not conduct. And in general, the reciprocity theorem is stated like this. You have a network N which is a reciprocal network, Any network which obeys reciprocity theorem is called a reciprocal network, but then you cannot define reciprocity theorem in terms of reciprocal network. So you say N contains linear elements, linear and bilateral elements. N contains only linear and bilateral elements. It is a two-port network, and therefore if you apply a voltage source, I am going to ask you a question now. If you apply voltage source here and measure the current, the same network, if you measure the current here due to a voltage source here, while the ratio is the same, that is I1 by V1 is equal to I2 by V2, that is the transfer admittances are the same, then the network N, well, this is a statement of the reciprocity theorem, that if the excitation and the response are interchanged, there is no change in the ratio. All right. If this is 1 volt and this is 1 ampere, this is 50 volts, then this should be 50 amperes. The ratio shall be the same. Now I am asking you a question. Look at the question carefully. Suppose, well, under this condition, suppose I apply a current generator. All right, let's say I1, and I measure the voltage V1 here. Similarly, I apply a current generator I2 here and measure the voltage response V2. By reciprocity theorem, the ratio should be the same, that is response to excitation should be equal to the response to excitation. If N is a linear network with bilateral elements, then the ratio of the response to excitation should be the same as the ratio of the response to excitation. If I call this, if I characterize this in terms of transfer admittances, response is a current, excitation is a voltage, current to voltage is admittance, and current and voltage are at different ports, and therefore we say Y12 is equal to Y21. Then what should we call this? Transfer impedances. Z12 should be equal to Z21. The question that I ask is there a relationship between Y12 and Z12? They are reciprocals of each other? Much to your frustration, they are not. They are not, and this is something which we wish to investigate. What is the relationship between? They are not simply the reciprocals of each other. Why? What is the reason? The reason is that the conditions here are quite different from conditions here. There is a short circuit and there is an open circuit. They are dual situations, all right, but they are not. The impedance and admittance are not reciprocals of each other. One must remember this, that Yij is not equal to Zij. Transfer impedance. Okay. All right. This must be remembered, because this is a mistake very often committed even by graduate electrical engineers. So you should be particularly careful about this. To investigate this point, relationship between the transfer admittances, we consider a two-port in general. Let's say capital N is a two-port, a general two-port, where what you can do is you can apply a voltage. What are the things that you can do? You can apply two voltage sources and measure the currents. You can't reach inside the network. You have only two ports, all right. So all you can do is you can apply two voltage sources, measure the current, or you can apply two current sources and measure the voltages, or you can apply a combination. One of them can be a voltage source, the other can be a current source, and you can measure one voltage and one current. The fact of the matter is that there are four quantities, V1, V2, I1 and I2, of which two can be specified independently. The other two then shall be determined from the characteristics of the network N. Is this clear? There are 4 quantities, 4 parameters, or 4 variables, of which 2 can be independently specified. Other 2 will be determined by the characteristics of the network. In how many ways can you specify the independent and the dependent variables? Obviously there are 6 ways. 4C2, 2 taken out of 4. So factorial 4 divided by factorial 2, which is 4 times 3 times 2 divided by 4, so 6 ways. Alright. Now 6 ways means what? You can say V1 and V2 can be a set of dependent variables. V1 can be, let's say, F1, I1, I2. V2 can be F2, I1, I2. These are independent variables, I1 and I2, and V1 and V2 are dependent variables. Or you can write I1 and I2 in terms of V1 and V2, 2 voltage sources, and then you find the dependent currents. Or you can make a combination, V1 I1, V2 I2. You can make V1 I2, V2 I1, or their permutation. You can have V1 I1, or you can have I1 V1. All right, that's also a possibility. There are in all 6 ways, but at the present time, we shall concern ourselves with only 2 of these representations, that is V1 V2 in terms of I1 I2, or the other way around, that is I1 I2 in terms of V1 V2. All right, and since the network, what we mean is V1 is expressed as a function of I1 and I2, V2 is expressed as a function of I1 and I2, or I1 is expressed in terms of V1 and V2, I2 is expressed in terms of V1 and V2. All right. Now, the network is linear. And therefore V1 shall be of the form K1 I1 plus K2 I2, and V2 shall be of the form K3 I1 plus K4 I2. All right. It's a linear network, and therefore the voltage and the current, the voltage which is a dependent variable, must be a linear combination of I1 and I2. That is if, pardon me, superposition. That's it. I1 and I2 are independent variables, they are sources, and therefore you can determine the responses to each independently, then add them up. Similarly, you can write I1 equal to K5 V1 plus K6 V2, and I2 as K7 V1 plus K8 V2. All right. Now, if the network is excited by sinusoids, that is AC sources, then a special form of these relationships are valid, and these special forms can be obtained by very simple considerations. What is the dimension of K1? It must be impedance. Similarly, K2, K3, K4, all of them should be impedances. Agreed? So what I do is, if we take the first set of relationships where I1 and I2 are independent variables and V1 and V2 are dependent variables, then we say the voltage phasor V1 and the voltage phasor V2 can be written as in terms of I1 and I2, similarly I1 and I2, and the coefficients are impedances. So we shall have Z, 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 Z. We must now specify all Z's, we must now distinguish between the 4 Z's. All right. Now what shall we call this? What shall we call this Z, for example? Well, we call this Z11, and the reason is the following. The reason is that what is Z11? It is V1 divided by I1 with I2 equal to 0. Now V1 by I1 means that you are measuring the response at the same port as the excitation. Isn't that right? If you recall, this is port 1, this is V1 and this is I1. What you are doing is you are making I2 equal to 0. I2 equal to 0 means these are left open circuit, and therefore you are applying a current source here and measuring the voltage. Isn't this a driving point impedance? Driving point impedance, and since it is measured at port 1, we call it Z11. Question is, why two subscripts? Well, two subscripts are needed because the transfer impedances require two subscripts. So to keep uniformity, we maintain two subscripts for the driving point impedances also, and from the same consideration this will be called Z12. The current is measured at port 2. Okay, I intentionally, it's okay. If you agree, then I will not explain further. It's a matter of convention. This impedance is called Z12. If I had introduced a different convention, go back and change it. All right. What should we call this? Now, before we go to the other one.
So, but I2 is the independent one. Yes, sir. So it should be Z21.
Okay. I2 is the independent variable.
Yes, sir.
And I am measuring V1. Under what condition? I1 equal to 0. So Z12 is equal to V1 divided by I2. All right. And we call this Z12. That is from response at port 1 and excitation at port 2. If I had used a different nomenclature earlier, go ahead and change it. All right. This is the IEEE accepted terminology, universal terminology. Similarly, this impedance we shall call Z21 and this impedance we shall call Z22. You understand why double subscripts? Z, we could have called this Z1, we could have called this Z2, but since we have to use double subscripts for the transfer impedances, we maintain uniformity. And you see that if the network is reciprocal, then what is the condition? Z12 should be equal to Z21. All right. If the network is reciprocal, if the reciprocity theorem is obeyed, then this should be satisfied. What does this mean? That in order to describe a two-port, we do not require 4 parameters. We require only 3, provided the network is reciprocal. Suppose this network has a transistor. Transistor can be considered as a combination of diodes plus an amplifying element, which are unilateral elements, and therefore it will not be valid there. In the case of a transistor amplifier, Z12 equal to Z21 is not valid. They are quite different. One is much larger than the other. But in the case of a passive reciprocal network, that is a network containing linear and bilateral elements, this shall always be valid. Tomorrow we shall consider the other kind of description, that is considering voltages as independent variables and currents as dependent variables, and then establish a relation between Y12 and Z12.